Hello and welcome to another exciting segment of Math with Miss Bennett. Today we're going to just be discussing area. Area is the space that's inside of a two-dimensional figure. It's always measured in square units or units squared. Area is not length times width. That is a formula for calculating the area of a rectangle. Very important. Area itself is the generic space inside of the 2D figure. So I've got space here in the big cloud. There are three ways to find area. We can count squares if we're given the grid lines. We can use a formula if we know the formula for the shape. And we can decompose the shape we have into known shapes and find the area using those known shapes. Here we have a rectangle and we're asked to find the area. You're probably familiar with this, but you could take and count out all the units. 1, 2, 3, 4, 5, 6, 7... and so on all the way out to the end, which ends us at 28. So the area is 28 square units. And shortened, of course, we could find the length, 1, 2, 3, 4, 5, 6, 7, and find the width, 1, 2, 3, 4, and use the idea of an array to say the area is 7 times 4, making the area 28 units. This is, of course, where the rectangle area formula comes from. Area equals length times width. I didn't put a multiplication symbol in there because in algebra we can put two letters or variables next to each other and it means multiply. We're going to take that formula we know and apply it to something else. Here we have a parallelogram. I know it's a parallelogram because it has four sides. The two opposite sides are parallel, meaning their lines go on forever and would not ever intersect. They would never meet. And you'll notice that the two sets of sides, the two opposite sides, they're also equal. This is what defines it as a parallelogram, not just that stereotypical shape. And I specifically drew this one sideways, or what we might feel like is sideways, to get us to see past our mental image of a parallelogram. So finding the area of this would be a little bit tricky. We could break this up a little bit and make it a rectangle. We could count the squares, and in this rectangle I have 1, 2, 3, 4, 1, 2, 3, 4, 5. 4 times 5 is a total of 20. And then I'd have to work with the other pieces for 1, 2, 3, 4, 5, 6. So I have 20 plus 6, and then some, this one and that one together maybe make a whole. This one and that one together maybe make a whole. And these together maybe make a whole, and those maybe. And just kind of get an estimate by adding things up. There's got to be a better way. Also, another way to write square units is to put the little squared symbol, the raised up exponent 2, on the end of units. Let's decompose instead. Let's turn this parallelogram into a shape we recognize, a rectangle. So I'm going to take this entire piece right here, this entire triangle, and I'm going to slide it down, straight down, because it kind of looks a lot like the missing piece here at the bottom. So if I take the shape I now have and mark it carefully, you'll see a rectangle. And I know how to find the area of a rectangle. I simply need to find the length measurement and the width measurement and multiply them together. So I'm going to find the length measurement, 1, 2, 3, 4. And the width measurement, 1, 2, 3, 4, 5, 6, 7, 8. And I get 32 square units. And the interesting thing about this is that it works for any parallelogram out there. You've seen it in other examples, I'm sure, but no matter how the parallelogram is turned, oriented, how fat or thick or thin or long or short it is, this method of decomposing it back into a rectangle works. For this reason, there's a formula for the area of a parallelogram. Here I have a parallelogram and I have its base measured out in brown. Notice that the base could be either the bottom or the top, and I have its height here in red, and you'll notice that the height isn't a side. You'll notice that the height is often shown with a little dotted line. You can either find the height inside the parallelogram or outside the parallelogram, but the important thing for the height is that it always comes with a right angle. Meaning, no matter how they turn the shape, even if your parallelogram is going crooked like this, the base and height are still going to be found by looking for that right angle. So there's the right angle, there's the height and the base. If you know the base and height, you can just apply the formula area equals base times height. This formula is technically the same formula as length times width. However, the height is not going to be a side of the parallelogram. Thus, we use a different formula. You will see a lot of math teachers do a rectangle with the formula area equals base times height. And those are math teachers in 7th grade and up because they're accustomed to using that formula for other shapes. So some of them have just kind of let the elementary school length times width formula go on and just use this one instead because it works for both. Here I've got a parallelogram very specifically turned sideways just to get you accustomed to seeing it in different orientation. I need to find its area. So I'm going to take a look at this, and I notice that I've got 3 different measurements. I've got 18, 4, and 5. One of these measurements is not needed to find the area. That would be the slanted side. I don't need to know that in order to find the base and height, because remember, for the base and height, I look for that right angle. So I see 18 and 4. They meet at a right angle. This is a right angle too. So its area, base times height, is 18 times 4. And I can break that down to the distributive property. 4 times 10 is 40. 4 times 8 is 32. And add that together, you get 72 units squared. What about triangles? Here I have a right triangle. I could, like I did with the rectangle and the parallelogram, try to make an estimate. So I could count up what I do have. This here, I see a 2 by 4, so that's a total of 8. Here's 9, 10, 11, 12. And then I kind of just have to do some estimating. Maybe an area of approximately 14 units squared. But of course, there's a better way to go about it. Here I've got the exact same triangle. You can count out its base is 1, 2, 3, 4, 5, 6, 7 units. And its height is 1, 2, 3, 4, 5 units. Exact same as the one above. If I didn't yet know a formula for the area of a triangle, I do know that I could double this up and make it into a rectangle. If you can't see it, I'll show you. So if I look at this new triangle I put here in orange, I can count out its height. 1, 2, 3, 4, 5. And I can count out its base. 1, 2, 3, 4, 5, 6, 7. Exact same triangle. 2 copies of the exact same right triangle put together, rearranged, rotated, make a rectangle. Thankfully, I already know that the base and height of the rectangle are 7 for its base and 5 for its height, because it shares its base and its height with the triangle. So if I know the area of the rectangle, length times width, 7 times 5, then I know the rectangle area is 35. Thus, the triangle, which I made a rectangle by doubling, I would need to half this area for the area of the triangle. So half of 35 is 17.5, or 17 1/2. And thus you can actually find the area of a triangle by turning it into a rectangle. But what if my triangle isn't a nice right triangle? What if it's an obtuse triangle? Take a look at this obtuse triangle. It has an obtuse angle. The other 2 angles are acute. And because of that, it's probably a scalene obtuse triangle. If I look at these 2 lines on the sides here, they don't appear to be equal, and they're definitely shorter than the other side. How am I going to make this into a rectangle? Well, I'm not. What I'm going to do instead is carefully reflect this shape or mirror it across the long side. If doubling a right triangle, reflecting it across the long side, makes it into a rectangle, let's see what happens if we double by reflecting this obtuse triangle. To make sure I get my dimensions right, I'm going to count them out. I need this shorter side to be over here. So I'm going to figure out that it is 1, 2, 3, 4, 1, 2 away. So in drawing my reflection, it's going to be 1, 2, 3, 4, and then 2 away. 1, 2. Making the lines land there. And then I'll finish the other side by connecting. And there you have it, 2 copies of the exact same triangle. And what does this create? This creates a parallelogram. And we know how to find the area of a parallelogram. We use the area formula, base times height. So if I find the base, 1, 2, 3, 4, 5, 6, multiply it by the height, 1, 2, 3, 4, I get an area for the parallelogram of 24 square units. If I made the parallelogram by doubling the triangle, then the triangle area is just going to be half of that. 24 divided by 2 is 12 square units. Let's do this one more time. Here we have an acute triangle. we need to find its area. So we're going to do the same thing we did, and we're going to mirror or reflect this across one of its sides and create a parallelogram. I'll count it out that the other side needs to be 1, 2, 3, 4, 1, 2, 3 over. And if I count out the flat side of the triangle, which I'm going to call its base, and it doesn't have to be the bottom, I get 6. So I'm going to count out 6 to here and put my dot there. Then, knowing that my height's going to stay the same, that 1, 2, 3, 4, 1, I can connect them, and I'll have 2 copies of the same triangle, thus making a parallelogram. There's a chance this could be a rhombus, but because we don't know for sure and I don't want to get out a ruler, I'm going to call it a parallelogram. Note that the base and height of this parallelogram match the base and height of our triangle. There's 6 and 1, 2, 3, 4, which we can measure inside or outside. Let's measure it outside to get us used to that. So if the area of the parallelogram is base times height, 6 times 4, its area is 24. And to find the area of the triangle, we simply half it, because the triangle is made of half of the rectangle. It's 12 square units for 24 divided by 2. Of course, it is totally coincidental that I made 2 different parallelograms and 2 different triangles, and they both got 24. It's just what looks good and is easy to count drawing out. But the key thing to take away from this is that we can find the area of a rectangle or a parallelogram by using the formula area equals base length times height length. In a rectangle, the base and height will both be a side. But in a parallelogram, one will be a side and the other one will be some other measurement from the inside or the outside that meets at a right angle. And by multiplying those 2 measurements, we'll have the area of the shape. And then for right triangles, be they any kind, right triangles, for acute triangles, or obtuse triangles, we have the formula for the base rectangle or parallelogram that it's part of, base times height. And then because the rectangle or parallelogram is double the triangle, we would half it. So in these shapes, the bases are often one of the sides, here's a base, there's a base, and there's a base. They don't have to be on the bottom though. And the height, again, comes at a right angle. In the right triangle, the height is a side because it's a right triangle. In some acute triangles, you'll see, and other triangles, but mostly in acute triangles, you'll see the height going from the tip, the tall tip, down to the bottom, and there's our height. And in our more obtuse triangles, there is no straight line down, no space to do it inside, so we often give the measurement from the outside. And we just show that it connects to the base at a right angle. And the lines will be dotted because they're not actually a part of the shape. So we've learned two formulas, and we know now that those two formulas cover squares, rhombi, which is the plural for rhombus, rectangles, parallelograms, and all of our different types of triangles. Again, just in case we don't know, a square is a special type of rectangle. It meets all the requirements for a rectangle, but the two pairs of sides that are equal, both pairs also happen to be equal. Same for a rhombus. It meets all the requirements for a parallelogram that has two equal sets of parallel sides and four sides, but those two side pairs are actually also equal to each other. I know this was a longer segment of Math with Miss Bennett, but I wanted to give you a very detailed description of why the area for a rectangle, parallelogram, square, and rhombus is base times height, and the area for a triangle is base times height divided by 2. Thanks for joining me.